Hello everyone. In today's lecture we'll move to a new chapter, which is the discrete Fourier transform, or the DFT. So far in this course we have been dealing with discrete time signals x of n, which are defined for the entire time domain, defined for n going from minus infinity up to positive infinity. And we have seen transforms like the Z transform, in which we compute x of z as a summation going from n equal to minus infinity up to positive infinity of x of n times z to the power minus n, which means that x of z contains information about x of n defined for all time, for n going from minus infinity up to positive infinity. And we have seen that if we replace z by e to the power j omega, which is equivalent to going around the unit circle, setting r equal to 1, we get the discrete time Fourier transform, the DFT, which is defined as the summation going from minus infinity to positive infinity x of n e to the negative j omega n. Again, x of e to the power j omega contains information about x of n for the entire time domain, for n going from minus infinity to positive infinity. From the computational point of view, when we try to compute these kind of summations going from minus infinity to positive infinity, we face a problem. For instance, if you try in MATLAB to define a signal x of n extending from minus infinity to positive infinity, as a matter of fact, you cannot. You can in MATLAB define a finite duration sequence starting at certain time instant and ending at another time instant. Generally speaking, in any computational platform, you cannot define an infinite length sequence. You cannot ask the computing device to compute a summation going from minus infinity to positive infinity. What you can do, on the other hand, you can do a finite summation. You can ask MATLAB to define a finite duration sequence and to sum finite number of samples. That's why, instead of defining a signal extending from minus infinity to positive infinity, we choose a window, a part of this signal that we will be dealing with at a time. So, for instance, instead of defining x of n as extending from minus infinity to positive infinity, we will define a window starting at instant 0, ending at some point, let's say 3 over here. Choosing this part of the signal, we will only be dealing with finite duration sequences and finite summations. So, as you can see over here, we will be dealing with only a finite portion of the signal x of n. So now we'll be dealing with samples from 0 up to 3, and the next frame we'll be dealing with 4 up to 7, and so on. We will divide x of n into frames, if you wish. And each frame will have a length of n samples, starting at 0 and ending at n minus 1. And this is basically what's happening in discrete Fourier transform. In DFT, we define what's called an n-point DFT, which is defined as summation starting at n equal to 0 and ending at n minus 1. So instead of having infinite sum going from n equal to minus infinity to positive infinity, here we have a finite sum going from n equal to 0 up to n minus 1. X of n times e to the negative j 2 pi over n kn. And as you can see over here, if you compare this expression we have with e to the negative j omega n, let's try to compare them. So let's compare e to the negative j 2 pi over n kn with e to the negative j omega n, the expression we have in computing the discrete time Fourier transform. The main difference over here is the definition of the frequency. As you can see, here we have n, which corresponds to this n, and negative j as well. The one difference over here, in discrete time Fourier transform, omega is a continuous variable, whereas in the discrete Fourier transform, omega has been replaced by 2 pi over nk, which is kind of a discrete frequency. So The main difference between the discrete Fourier transform and the discrete time Fourier transform are as follows. The first difference, that we have a summation going from n equal to 0 up to n minus 1 instead of summing from minus infinity to positive infinity. The second difference is that the frequency omega is replaced by a discrete frequency 2 pi over n times k, as if we have sampling in the frequency domain. So over here, as we can see, in the discrete time Fourier transform, the DFT, we are using a continuous variable frequency omega. And as we have discussed before, omega becomes periodic. Since we have a discrete time signal, the frequency domain becomes periodic every 2 pi. So the discrete frequencies we are talking about takes the form 2 pi over n times k. So as if we have divided this entire range from 0 to 2 pi, one cycle, 2 pi over n. So we have n steps, resulting in delta omega equal to 2 pi over n. So as if we have divided one period in the frequency domain of length 2 pi into n steps, n equal steps. Each has width of 2 pi over n capital. Multiplying by k, so 2 pi over n, which is delta omega. Delta omega times 0 will give us a frequency of 0. And delta omega times k equal 1 will give us the first sample over here, times 2, the second sample, and so on. So again, we have replaced omega, the continuous variable we have, by 2 pi over n, which is delta omega, the step we have in frequency between two consecutive samples, times k. And k now becomes the new frequency, the discrete frequency. And this is similar to what happened in sampling in time domain. We started with a continuous time t. We performed sampling every ts. So we have sample at 0 ts, 2 ts, 3 ts, which is n times ts. And then we replaced ts by 1 or normalized with respect to ts, and now we have the new time, which is n. Same here in frequency, we did sampling in frequency domain, so we will replace omega by k, where k is the index of the frequency domain right now. So in discrete Fourier transform, we sort of have sampling in frequency domain. And instead of using a variable called omega, we have a variable called 2 pi over nk, discrete frequencies, discrete omega, taking samples at 0 and delta omega and 2 delta omega and 3 delta omega and so on. And as you can see over here, when we go to sample number n, this will correspond to 2 pi. Okay, and maybe we have discussed this before, that sampling in one domain results in periodicity in the other domain. So over here, since we did sampling in frequency domain, we will be getting periodicity in time domain. So signals in discrete time Fourier transform will be seen as periodic in time. And we will use the notation x tilde of n. We'll add this tilde over here to indicate that the signals are periodic or are seen as periodic in time domain. And this is basically a result of the sampling we have in frequency domain. This periodicity in time domain is defined by the equation x tilde of n is equal to summation x of n minus l n capital, where l goes from minus infinity to positive infinity. This equation is kind of out of scope. If we have enough time, we will go through it and we will actually prove it. But for now, just keep in mind that since we have discreteness in frequency domain, we have sampling in frequency domain, we have periodicity right now in time domain. And this periodicity is defined by this equation, which we do not need to worry about that much. If we have enough time, we would have gone through it in details. And this basically will result in what's called time domain aliasing. It's basically happening because if you consider the equation, x of n minus ln is the shifted copy of x of n, and shifted by n capital. So if l is equal to 0, you will get x of n. If L is equal to 1, you will get x of n minus n capital. If you get L equal to 2, you get x of n minus 2n capital, which means that x tilde is kind of repetition of x of n shifted in time. So if this is x of n's original signal, which has a spectrum x of e to the power j omega, and then we decided to sample the spectrum in frequency domain in order to use DFT. This will result in periodicity in time domain. So first let's set L equal to 0. So x of n will be replicated as is, the one in black over here. And if we set L equal to 1, so L equal to 1, we will get x of n minus n capital. So you will get this curve, L equal to 1. And if we set L equal to 2, we will get this green curve. This is L equal to 2. And if we set L equal to minus 1, we will get this one, this curve, L equal to minus 1, and so on. And of course, the black one is L equal to 0. And this goes from minus infinity to positive infinity. And now we can see that there is sort of overlap between samples. So we have green samples from L equal to minus 1 here in the black interval. And we have samples from this black cycle into the green one, and so on. This is called time domain aliasing. Again, don't worry so much about this part. It needs lots of time to be explained. We don't have such time. So for now, keep in mind in DFT we have discreteness in frequency domain, which results in periodicity in time domain. Okay, so let's move back to our slides over here. So in discrete Fourier transform, we deal with n consecutive samples, as we have said before over here. Instead of dealing with x of n extending from minus infinity to positive infinity, we choose a window starting at 0, ending at n minus 1, as you can see over here, from 0 up to n minus 1. So, given n consecutive samples of x of n, defined from n equals 0 up to n minus 1, of a periodic or aperiodic sequence, which is basically any sequence. So the n-point DFT, discrete Fourier transform, which is defined as x of k, where k is also discrete, going from 0 to n minus 1. As we've seen over here, k, which is a frequency index right now, it also goes from 0 up to n minus 1. Why not up to n? Because n will correspond to 2 pi, and as we have discussed before, the frequency domain is now periodic, and 2 pi is a repetition of what's happening at 0. So n capital is a repetition of what's happening at k equals 0. So one cycle will start at 0, ending at n minus 1. So x of k is defined as summation from 0 up to n minus 1 of x of n e to the negative j 2 pi over n kn. And as we have seen over here, the main differences between the definition of the DFT and the definition of the discrete time Fourier transform, the DTFT, that the summation goes from 0 up to n minus 1 instead of going from minus infinity to positive infinity, which means in DFT we'll only deal with one frame of finite length starting at 0 ending at n minus 1. And the second difference, instead of dealing with continuous frequencies omega, we will deal with discrete frequencies defined as 2 pi over n times k. And why do we need to deal with discrete frequencies instead of continuous frequencies? Again, because working with digital devices, using digital computation and tools like MATLAB, we cannot define a continuous variable. We need to define only, or can only define discrete variables. That's why we cannot work with omega, but we can work with samples of omega. So the definition of the endpoint DFT goes as follows. X of k, which are called the DFT coefficients, equal to summation n equal to 0 up to n capital minus 1 x of n e to the negative j 2 pi over n capital times kn, where again we are only considering n capital consecutive samples of the signal x of n, starting at 0, ending at n capital minus 1, and replacing the variable omega by discrete frequencies 2 pi over n capital times k. Now, given these n DFT coefficients, x of k, again x of k are called the DFT coefficients, we can compute the inverse discrete Fourier transform. That is to compute x of n. X of n is equal to 1 over n capital, summation over k going from 0 up to n minus 1. Again, k here is the frequency index. X of k e to the power j 2 pi over n capital k n. And this is the equation of the inverse discrete Fourier transform. So we have a sequence x of n in time domain defined for n instance from 0 up to n minus 1. We compute the so-called n-point DFT, and we get x of k where k is also defined for k from 0 up to n minus 1. So the length of the sequence x of n and the length of x of k are equal to each other. They both have the length of n capital. X of n is the sequence in time domain. X of k are samples of the spectrum of the signal we have. So x of k is a function of the discrete frequency index k. K is a discrete frequency index resulting from sampling in frequency domain, dividing the 2 pi fundamental period we have in frequency domain into n equally spaced samples, n capital equally spaced samples. So omega k is equal to 2 pi over n k, and delta omega, the step between any two consecutive samples, is 2 pi over n. The discrete Fourier transform is discrete both in time and in frequency. In time we have the time index n, which only takes integer values, so we have discrete time, and in frequency domain we have the frequency index k, which means we have integer values of k, we have discrete frequencies only, as opposed to the discrete time Fourier transform, the DTFT, in which we have discreteness in time, but the frequency domain is continuous. If we go back to the definition over here, the discrete time Fourier transform, in time domain it's discrete, x of n, but in frequency domain it's function of a continuous variable called omega, whereas in the DFT, the discrete Fourier transform, we have discreteness both in time and in frequency. So let's define the complex quantity w suffix n, which is known as the Twiddle factor. W suffix n is defined as follows: e to the negative j 2 pi over n capital, which is the term appearing in the definition of the DFT and the inverse DFT. So the definition of the DFT coefficients x of k can be computed as a summation from n equal to 0 up to n capital minus 1 x of n wn to the power kn, where wn is e to the negative j 2 pi over n. So w is a complex quantity. And again, n and k are only defined for range from 0 up to n minus 1. And same for the inverse DFT, where x of n can be computed as 1 over n capital, summation from k equal to 0 up to n minus 1 x of k wn to the minus kn. So the DFT uniquely describes n consecutive samples of x of n in time domain by n consecutive samples in frequency domain, x of k. And by uniquely, we mean that from x of n we can get x of k, and from x of k we can get the same x of n back. So wn to the power k are equally spaced vectors on a unit circle with angular spacing of 2 pi over n. So in order to understand this statement, let's go to our whiteboard over here. So wn is defined as e to the negative j 2 pi over n, again dividing a 2 pi angle by n capital. So let's assume n is equal to 4, and we get w4, which is equal to e to the negative j 2 pi over 4, or e to the negative j pi by 2. So now let's consider the quantity w4 to the power k. It will be e to the negative j pi by 2 times k, and k will take the values from 0 up to n minus 1. n is 4 in this case, so k will take the values from 0 up to 3. So considering the first value of k equal to 0, we will be having w4 to the power 0, which is 1, which is a complex number of magnitude 1 and angle 0. real part equal to 1, imaginary part equal to 0. So in the complex domain, if this is the real axis, this is the imaginary axis, and if we have a circle like this of radius 1, so the first quantity, W4 to the power 0, will be a vector of length 1 and angle 0, real part equal to 1 and imaginary part equal to 0. This is W4 to the power 0. Moving to the next value of k equal to 1, we will be having W4 to the power 1. Going back to the definition, we will be having e to the negative j pi by 2, which means we have a complex number whose magnitude is 1 and whose angle is minus pi by 2. So going to the complex domain, we will have this vector of magnitude 1 and of angle minus pi by 2. And this would be W4 to the power 1. Moving back over here, so when k is equal to 2, we will be having W4 to the power 2, which is e to the negative j pi by 2 times 2, which is minus j pi, which is a complex quantity whose magnitude is 1 and whose angle is minus pi. So it will be like this, a vector pointing in this direction. This is W4 to the power 2, and this angle is minus pi and magnitude is 1. Moving to the next value, which is k equal to 3, we will get W4 to the power 3, which is e to the minus j 3 pi over 2, which is a complex number whose magnitude is 1 and whose angle is minus 3 pi by 2, this angle. And this would be W4 to the power 3. What about W4 to the power 4? What if we set k equal to 4? In this case, we will be having W4 to the power 4, which is e to the negative j 2 pi, which is 1. But 1 was W4 to the power 0. So as you can see over here, W4 to the power 0 is equal to W4 to the power 4. And if you try with W4 to the power 5, you will get W4 to the power 1. So W4 to the power 5 is equal to W4 to the power 1. And so on. So as you can see, Wn to the power k is periodic, with period n capital. So we can reach this conclusion that Wn to the power k is periodic in k, with period n capital. Okay, so if we try to do this for n equal to 3, we will get these three vectors separated by an angle 2 pi over 3. If we try to do it for n equal to 6, we will get these vectors over here. It's very important that we know how to compute these values. This will help us computing the discrete Fourier transform. And of course, you can find values over here using Euler equation or even from the complex domain. So for instance, W4 to the power 1, which is e to the negative j pi by 2, will be simply equal to minus j. And e to the minus j pi will be 1, minus 1. And e to the negative j 3 pi by 2 will be positive j. So you can compute the values of these complex numbers either using Euler's equation or directly from the complex domain. It's very straightforward. So let's try to solve this example in order to apply the definition we have seen for the DFT. So here we have a signal x of n, which is only one sample, which is only delta of n. And we need to compute the discrete Fourier transform of this unit sample. So here we have a signal x of n, which is equal to delta of n, and as you can see over here, it's just one sample of value 1 at instance 0, and it has 0 values otherwise at 1, 2, and 3, and minus 1, and so on. So first, let's try to find the spectrum of this signal using the discrete time Fourier transform. The definition of which is very simple. It's x of e to the power j omega is equal to summation from minus infinity to positive infinity of x of n times e to the negative j omega n. And as you can see, the signal x of n we have over here has only one non-zero sample. So this entire summation will give us 0 except at n equal to 0. At n equal to 0, we will be having x of 0 times e to the minus j omega 0. So x of 0 is 1 and e to the minus j 0 is 1. So the spectrum of this signal using the discrete time Fourier transform is 1. And if we try to plot this as a function of the variable omega, it will be simply some sort of a constant value 1 for all frequencies. And this would be the spectrum x of e to the power j omega. Now let's try to compute the n point DFT. So if you want to compute the n point DFT, the definition goes like this. So x of k will be summation, and instead of going from minus infinity to positive infinity, we will go from n equal to 0 up to a certain n minus 1. We will choose a window in time domain, and we'll be summing x of n e to the negative j 2 pi over n times kn, where also we have replaced the continuous frequency omega with discrete frequency 2 pi over nk. This is equivalent to taking only a window of the signal, and instead of working with the entire time domain, we only choose a window extending from 0 up to n minus 1. So let's see the implication of the DFT and how does x of k relate to the spectrum we have x of e to the power j omega. So again, x of n is 0 for the entire time domain except at n equal to 0. So this summation will only have one value, which is x of 0 times e to the power 0, e to the negative j 2 pi over n capital k times 0. This will give us 1. But this one is completely different from the one we got in the DTFT. How is that? The one we got here is for a function called x of k, and this is true for discrete values of k, where k takes the values from 0 up to n minus 1. Whereas this continuous variable omega takes the values from minus infinity to positive infinity in a continuous manner. It's a continuous variable. That's why when we plot x of e to the power j omega, it was a continuous function like this. But right now, when we plot x of k, it will be sort of discrete function. At k equal to 0, we have a value of 1. At k equal to 1, we have a value of 1. So the values will be 1 for all k. So as you can see, x of k is kind of samples of x of e to the power j omega, the concept of sampling in frequency domain. So as if we are taking samples of x of e to the power j omega, and the spacing between every sample and the next sample is delta omega, which is 2 pi over n. So now we can understand that the DFT is kind of sampling in frequency domain of x of e to the power j omega. And instead of working with a continuous variable omega, which we cannot in digital environment, now we have samples in frequency domain, we have x of k. So computing the DFT is like computing samples of the spectrum of the signal we have over here. So moving back, x of k is a summation from n equal to 0 up to n capital minus 1, x of n w n to the power kn. Doing the summation, we will get 1 for k from 0 up to n minus 1. And we can do the inverse as well. We can compute x of n from x of k. So 1 over n capital, summation from k equal to 0 up to n capital minus 1, x of k, which is 1 in this case, wn minus kn. 1 over n summation wn to the power minus kn. How can we compute this summation? Let's move to our whiteboard and see how it goes. So the definition of the inverse discrete Fourier transform is x of n equal to 1 over n capital summation from k equal to 0 up to n minus 1, x of k wn to the power minus kn. And in this example we have x of k is equal to 1. So x of n can be computed as 1 over n summation going from k equal to 0 up to n minus 1, and x of k is equal to 1, and we will write wn in this form, wn to the power minus n all to the power k. And in this case we have the x of n summation in the form of the summation we have seen before. So this will be 1 over n, and this summation takes the form r to the power k. So we'll get 1 minus r over here, 1 minus w n to the power minus n. And in the numerator we'll be having 1 minus r, which is w n to the power minus n, all to the power n minus 1 plus 1, which is n capital. So let's consider the term appearing in the numerator, which is w n to the power minus n times n capital. This would be e to the power j 2 pi over n capital times n small times n capital. N capital will cancel out and we will get e to the power j 2 pi n, which is 1, always 1. So the numerator over here will always be 1 minus 1. So it will give us always 0. So this numerator over here will always be equal to 0, and hence x of n will always be 0, except for n small equals to 0. So x of n will always be 0 for all n except n equal to 0. Why is that? If you take a closer look and set n equal to 0, x of n will be 1 over n, and in the numerator you will be having 1 minus 1, which is 0, and in the denominator you will be having 1 minus wn to the power 0, which is 1, which will give you always 0. So x of n will be 0 over 0, which is undefined. In order to compute x of n at n equal to 0, we can go back to the definition of the inverse Fourier transform. So, doing so, we can compute x of 0 as follows. So x of 0 is equal to 1 over n, summation over k going from 0 up to n minus 1, x of k is 1, times wn to the power minus kn, and n small is 0, which will give us also 1. So 1 times 1 is 1. When you sum 1 from 0 to n minus 1, it will give you n capital. So it will be 1 over n times n, which is 1. So as you can see over here, this summation will always be 0 except for n equal to 0. At n equal to 0, it's 1. So trying to plot this function we got over here, we'll be having at instance 0 a value of 1 and zeros otherwise. And this is true for n going from 0 up to n minus 1, which is the impulse we started with in the first place. So this will give us delta of n for n from 0 up to n capital minus 1. So now we're ready to move on to the matrix formulation of the discrete Fourier transform. The definition of the discrete Fourier transform is a summation from n equal to 0 up to n minus 1 x of n wn to the power kn. Let's try to expand this equation as follows. So x of k would be equal to x of 0 times wn to the power k times 0 plus x of 1 times wn to the power k times 1 plus x of 2 times wn to the power k times 2, and so on until we reach the last term x of n capital minus 1 wn to the power k times n minus 1. And this equation will be repeated for k equal to 0 and k equal to 1 and k equal to 2 and so on. So what about k equal to 0? For k equal to 0, all the wn to the power k terms will give us 1s. So we'll be simply having x of 0 plus x of 1 plus x of 2 up to x of n minus 1. So let's go back over here. So x capital of 0, which is happening at k equal to 0, will be simply the summation of x small of 0 plus x small of 1 plus x small of 2 up to x small of n minus 1. So this can be arranged in this form. Let's have a column vector containing the samples in time domain x of n, x small 0 up to x small of n minus 1. And let's compose a matrix over here whose dimension are n capital by n capital. The first row of which would be wn to the power 0, where k is equal to 0. So it will be all 1s. So multiplying this first row times this column will give us x capital of 0, which corresponds to k equal to 0. What about k equal to 1? If k is equal to 1, we will be getting x capital of 1 equal to x small of 0 times wn to the power k times n. In this case, n is 0 and k is 1, so we will get wn to the power 0, which is 1. So x of 0 times 1 plus x of 1 times wn to the power k times n. N here is 1 and k is 1, so we will get wn to the power 1. And plus x of 2 times wn to the power 2 plus x of 3 times wn to the power 3 until we reach the last sample x of n minus 1 times wn to the power n minus 1. So if we go back over here, the second row will be 1 wn to the power 1 wn to the power 2 until we reach the last one, which is wn to the power n minus 1. When this row is multiplied by this column vector, we will get x capital of 1. If we set k equal to 2, we will get x capital of 2 equal to this row, the third row over here, which is 1 wn to the power 2 wn to the power 4 until we reach wn to the power 2 times n capital minus 1, multiplied by this column will give us x of 2 and so on. So as you can see, in order to compute the DFT using this matrix formulation, we first will create this column vector containing the samples x of n, which is n by 1 column vector. Next, we will compute this matrix, which is basically n capital by n capital. The first row corresponds to k equal to 0. The second row corresponds to k equal to 1. The third row corresponds to k equal to 2 until we reach the last row, which corresponds to k equal to n capital minus 1. And the first column over here corresponds to n equal to 0. The second column corresponds to n equal to 1 until we reach the last column, which corresponds to n equal to n minus 1. So if we assume n capital equal to 4, and let's try to construct this matrix. So as we've said, in this matrix it's n capital by n capital. So if n capital is equal to 4, so the matrix will be 4 by 4. The first row corresponds to k equal to 0, second row k equal to 1, third row, fourth row equal k equal to 3. And the first column corresponds to n equal to 0, n equal to 1, n equal to 2, n equal to 3. So in order to find the entries of this matrix, it's simply wn to the power kn. So in order to compute the very first value over here, it's wn to the power kn, where k is equal to 0 and n equal to 0. So w to the power 0 is 1. This entry will be wn to the power kn. Here k is equal to 0, n is equal to 1, so w to the power 0 is also 1. That's why the very first row will always be 1, because k is always 0. And the same for the first column. In order to find this value, it's wn to the power kn. K is 1, but n is 0. N is 0 for this entire column, so all the samples or the values will be 1. What about this value? This value would be wn to the power kn. In this case, k is equal to 3, n is equal to 3, so it would be wn to the power 9. And what about this value over here? This value over here would be wn to the power kn. K is equal to 2 and n is 3, so it will be wn to the power 6. And so on. So computing this matrix is actually very straightforward. It's just wn to the power kn, and the rows correspond to k going from 0 up to n minus 1, and the columns correspond to n going from 0 up to n minus 1. So x capital will represent x capital of k, capital W will represent this matrix, the DFT matrix, and this x small will be the time domain vector. So in order to compute the DFT coefficients, we will multiply the matrix W times x. Matrix W is n by n, the vector x is n capital by 1, and x capital is n capital by 1. So note that the DFT matrix is symmetric, and by symmetric we mean W is equal to W transpose, and by transpose we mean exchanging rows with columns. So if we go back over here, the first row is actually equal to the first column. The second row is equal to the second column. The third row is equal to the third column. So if you transpose this matrix, it will be the same. So W transpose is equal to W, and this is known as a symmetric matrix. In order to compute the inverse discrete Fourier transform in the matrix format, it's simply 1 over n capital W conjugate times x. So the time domain signal x small will be equal to 1 over n capital. The matrix W we have formulated, just take the conjugate, which is exchanging the sign of any imaginary part. If it's positive, make it negative. If it's negative, make it positive, times x capital. There is a proof for this equation, but it's out of scope. We will skip the proof, but I want you to know, in order to compute the inverse discrete Fourier transform in the matrix, the same matrix we have found, capital W, just take the conjugate, divide by n capital, multiply by x capital, you'll get x small, the time domain signal. So in MATLAB, the matrix W can be computed using the command DFT MTX. So DFT MTX is a DFT matrix, and you will give the command n capital, it will compute the matrix for you. Or you can use FFT of I of n capital. I of n capital will give you the identity matrix, which is ones along the diagonal, zeros otherwise, and FFT will compute the FFT or the DFT, and it will give you the same result, the same matrix Wn. So here we have an example. It's a very important example. It's simply asking you to compute the 4-point DFT of a sequence x of n, which is equal to 0, 1, 2, 3. So it's a 4-point DFT computation, so we need to find the matrix W4. So moving to our whiteboard over here, so we need to find the matrix W4. So it's basically 4 by 4 matrix. The first row is always ones. and the first column is always 1s, and the entry over here will be wn to the power k, and here this row corresponds to k equal to 1. As you remember, this is k equal to 2, and this is k equal to 3, and of course the very first one is k equal to 0, and the column over here corresponds to n equal to 1. So basically the first entry over here will be wn to the power 1, w4 to the power 1. The element next to it will be w4 to the power 2, where k is 1 but here n is 2. And the next one will be w4 to the power 3. And for the next row we'll be having w4 to the power. Here k is equal to 2 and n is equal to 1, so w4 to the power 2. Next w4 to the power, here k is 2 and n is 2, so w4 to the power 4. Next w4 to the power 6. And the very last row will be w4 to the power 3, and here w4 to the power 6, and here w4 to the power 9. So as you can see over here, this will be our matrix, and we need to compute the values of these w. Remember that w4 is e to the negative j pi by 2. So w4 to the power 1 will be minus j. w4 to the power 2 would be minus j squared, which is minus 1. w4 to the power 3 will be j. w4 to the power 2 will be minus 1. w4 to the power 4 is 1. w4 to the power 6 is minus 1. And here w4 to the power 3 is j. w4 to the power 6 is equal to w4 to the power 2, which is minus 1. w4 to the power 9, you subtract 2 4s, you will get w4 to the power 1, which is minus j. If you remember, w4 is periodic. w4 to the power k is periodic with period 4. So w4 to the power 9 is equal to w4 to the power 5 is equal to w4 to the power 1, which is minus j. So x capital, which is a DFT coefficient, will be equal to the matrix w times x small being the column vector containing the samples of x of n. So here we have the matrix w times the column vector including the samples of x of n. Doing the matrix multiplication is very straightforward, and this will be the DFT coefficient. Let's move to GNU Octave and see how we can do this in Octave or MATLAB. So first we defined x of n as a column vector containing the samples 0, 1, 2, and 3. Next we need to define the matrix we have w4, which is DFT mtx. This is a command in MATLAB that will give you the matrix, and giving it the dimension 4, so this will be the matrix we have. And as you can see, the first row is all 1s, the imaginary part is 0. The first column is all 1s, the imaginary part is 0. And the second row is 1 minus j minus 1 plus j, the same exact matrix we have computed on the whiteboard. Next, in order to find x capital, which is the DFT coefficient, it will be simply the matrix w multiplication with x in the time domain. And here we have w4. So we'll have these DFT coefficients, 6 minus 2 plus 2j minus 2 minus 2 minus 2j, which are exactly the same as the ones we got over here. And by the way, we can get the same result using the FFT command. FFT, fast Fourier transform, is an efficient algorithm to compute the DFT in a faster way. So FFT of x of n will give us exactly the same result, but supposedly faster. So in Octave or MATLAB, you can define x of n, w4, and then you can multiply w4 times x of n. If you want to do the inverse, it's simply 1 over n and you conjugate the matrix w multiplied by xk. Let's see how it goes. If you want to compute the inverse, it's simply 1 over n multiplied by the conjugate of the matrix w4 we have multiplied by xk. and n in this case is 4, so we'll get 0, 1, 2, 3, which is the original time domain sequence we have. So now we know how to compute the DFT and the inverse DFT in MATLAB and by hand, using the matrix formulation of the DFT.